So we're about to talk about work. And last year, we defined work to be F dot D, which in our case was F times D times the cosine, not of theta, but the cosine of the angle between F and D. So this year, though, we're going a step beyond, and we're going to say that work is, well, you've seen some calculus, right? Work is the integral of F dot dx, where this is a differential distance. So what we can do now is we can take some complicated path, and we can say at every instant there's a dx. That's the way that path is going. And if the force is some direction, like this direction or so, then every little bit of this, it's like a Riemann sum. We can be taking an integral. We can do every little bit of this along here and do the cosine for every single Riemann step that we do. And in principle, if we're taking an actual integral, it will be an infinite number of infinitely narrow steps. So we can expand this out a little bit. It is, in fact, the integral of f times the cosine of the angle between f and the direction we're going, integrated over x. So that's the way we're going to define work now. So this leaves us a couple possibilities. I mean, I guess it's three possibilities. The possibilities are this. We can have work greater than 0, we can have work equal to 0, and we can have work less than 0. Work is greater than 0 if the force, let's say it's this way, is, how are we going to do this? How are we going to do this? If that's our distance vector and that's our force vector, what are the requirements on this angle theta for work to be greater than 0? What do you think?
There has to be a...
How big can that angle get for work to be positive?
Up to 90 degrees?
Up to 90 degrees. So theta must be less than 90 degrees. What if the angle between force and distance is 90?
It's 0.
Ah, right. So that would be this case where force is, for instance, up, and the direction you're going is that direction, and you would have no work being done. And finally, we could look at the work being negative. That would be the case if the force is this direction, let's say, and the distance that you're going is that direction. So if theta, I guess if theta is in between 90 degrees, nope, that's not what it would be. If theta is less than 90 degrees and less than 180 degrees, oh man, this formatting is terrible. 180 degrees. Then we've got ourselves negative work, because this force is acting against the motion. Negative work seems to be slowing things down, and positive work seems to be speeding things up. But if the work is 0, what's the only thing that's happening if the work is 0? Hey guys in the back, if the work is 0, what's happening? I've got force at a right angle to distance.
Equilibrium.
It is not equilibrium. There is a net force at a right angle to the distance.
You say something going in a
Constant speed, but what's happening?
no acceleration.
No, there is acceleration.
Oh, there's a constant force, it's constant acceleration.
Constant acceleration, but not speeding up, not slowing down. What's happening?
No jerk.
All right. What is the thing doing?
So it's moving in a circle. Spinning.
It must be turning, right, Sam? Good work, good work. If it's turning, so let's see if we can draw ourselves a circular path, and we'll have the direction that the thing is going, that direction for an instant, and the force is always, oh, check it out, the force is always at a right angle, and I can call that a centripetal force also. So if we look over here, for some small instant it's going directly down. We could even call this, want to be fancy and call it dx. Yeah, I do too, because that makes it a little bit more calculus-y. We got dx there and dx right there. At this instant, while the thing is moving around in a circle going straight down, the force is still at a right angle to it, straight that direction. Cool? So a couple more things on work, and one of them is that we can say that work, if we're all going to have work, if we don't consider the integral form of work, then we can say that work is F dot D, just like last year. And then we can expand that and say, maybe we don't want the full force, we just want the force that's parallel to the distance. So we'll take the parallel force and multiply that by the distance itself. That eliminates that cosine, because there's a cosine in finding the parallel force. We could similarly say that it's the force times the distance that's in the parallel direction to the force. So these are equivalent because this parallel component of the force, or parallel component of the distance, includes the cosine of the angle between them in order to find it. So the next thing that I wanted to say is about this. If I have a bowling ball and I throw it up and catch it, there's a whole bunch of interesting stuff that's happening with work in the process. Let me first consider the bowling ball on its way up. That's its velocity. So the distance that it travels on the way up is upward. What direction is the net force on the bowling ball?
Upwards?
The net force on the bowling ball as it's going upwards in free fall is downward. So we want the force of gravity downward and the distance upward. So this equation here that says that work is force times distance times cosine of the angle between them is going to be negative. Work is less than 0. I have to be a little more careful than just saying work. I'm going to say work by gravity. As the bowling ball goes up, work done by gravity is negative. As the bowling ball falls, we have exactly the opposite situation. We've got velocity that's downward. We've got a distance vector that points downward. And which way is the force on the bowling ball as it goes downward? It's also downward. So the force on the bowling ball is downward. And now these suckers are parallel, the force and the distance that they're going. So the work by gravity is greater than 0. So gravity is increasing some kind of energy of the bowling ball over here and decreasing some kind of energy of the bowling ball right here. And I know that you know in your head which kind is which. So let's see. We've got negative work being done by gravity on the way up and positive work being done by gravity on the way down. In fact, if I throw it up and catch it, then they are exactly equal and opposite if I catch them at the same point. So the total work done by gravity, if it goes up and comes back down, the total work done by gravity is 0. And we could also call that net work. The net work done by gravity is 0 if it goes up from one height and it's in free fall and it comes back to that same height. Interesting. For the next experiment, I'd like to consider a falling microscope. You climb up on top of a ladder and you drop a microscope like this. And then you consider the microscope. Oh, it's hard to draw microscopes. They're like this, and they've got this stuff on them, and this other thing here. See, you knew biology would be useful at some point. You drop the microscope, and the microscope falls under the action of gravity, and gravity points down. Then the microscope is going downward, so is gravity doing positive work or negative work on the microscope?
Negative work.
Positive.
Positive work.
Because it's going in the direction of the microscope.
Yes.
So, since gravity is doing positive work on the microscope, we know the microscope is speeding up. Let's look at the acceleration of the microscope during the time that it falls. We can say that the acceleration, well, I guess it's going to be the net force in the microscope divided by the mass in the microscope. So it starts with some initial speed. If we consider like when the microscope was right here, it would have some initial speed, and then the initial speed goes to some final speed right before it crashes into the ground. During that distance d, it's sped up to Vf. So our plan is to take, well, we could find how these speeds are related by a tale of two squares. Remember that equation? It says Vf square equals V naught square plus 2 times A times the distance that the thing has fallen. And I'm just going to rearrange this equation a little bit. I guess I'll subtract V naught from both sides and then just flip the whole thing. I'm going to say 2AD is the final square minus the initial square. And now I'm going to take this definition of acceleration from Newton's second law, plug it in right here, and I've got check this out. 2 times F net divided by mass, see, that's just A plugging in right there, times D is equal to V final square minus the initial square. And now my plan is a slight rearrangement of this equation, which will lead me to, I guess I'm thinking I'll divide by divide by 2 and multiply by n. And I'll get F net times distance is equal to m over 2 times v final square minus v initial square. And that, see what's coming? I get 1/2 mv final square minus 1/2 mv initial square. This is the work kinetic energy theorem. But that doesn't make any sense unless we define what kinetic energy is. This is kinetic energy. And this is kinetic energy. But they're not just any kinetic energies. This one is the initial kinetic energy of the microscope, and this one is the final kinetic energy of the microscope. So notice that when work done is positive, if this term, this is net work is final kinetic energy minus initial kinetic energy. When net work is positive, that means final kinetic energy is bigger than initial kinetic energy. So the thing is speeding up. And when work net is negative, final kinetic energy must be smaller than initial kinetic energy. So the thing is slowing down. So you see the net work of the bowling ball on the way up. On the way up, the bowling ball is slowing down, so the net work is negative, and as the bowling ball falls, the net work on it is positive because it's speeding up. That's it. So power is work divided by time, and it's actually a pretty simple concept. We'll just define it as work divided by time, and that means that if you do some amount of work, let's say lifting a barbell or something, if you do it in a large time, you'll get a small power, and if you do it quickly in a small time, you get a large power. Another helpful thing is here we have a new definition of work. Work is now power times time. And so it is handy to remember because work is the power times the hour. If you're working in kilowatt hours, you know that kilowatts is a unit of power, and hours is a unit of time, and kilowatt hours is how Ameren bills us for electricity. For instance, I think at this point we're paying about 11 cents per kilowatt hour. A lot of people like to put a slash right there, like they're pretending it's kilowatts per hour. That would be crazy, because power is work divided by time. If you were dividing power by time, then you'd have work divided by time divided by time. You don't want to think about that. So this is our cost of electricity. I should probably also throw up a truth for you. There's this other stupid thing called a horsepower, and it's 746 watts, and that comes from the pre-industrial days, I guess. Maybe every once in a while you will see a motor described in horsepower or something. You might have a 1 horsepower motor or a half horsepower motor that's powering a power tool. So power is the rate at which energy is transferring forms. That's the idea. Let's define a kilowatt hour though. 1 kilowatt hour is equal to how many joules? Kilowatt hour is a unit of energy because it's the power times the hour, so it must be energy or work. If we make a little conversion here, we could say that, let's see, a kilowatt, it means that it's 1,000 joules per second. And then we're supposed to be multiplying that by, multiplying that by an hour, and an hour is 3,600 seconds. If we look at this, we've got 1,000 joules per second, that's this chunk right here, and 1 hour, 3,600 seconds. It looks like we're going to have 3.6 million joules. And another way to think of energy, of course, is 1 joule is the amount of energy required to lift 1 apple by 1 meter in Earth's gravitational field. With 3.6 megajoules, you could lift 3.6 million apples by 1 meter. Dang. And guess how much Ameren's going to charge you? 11 cents. That's it. Every little bit of this along here, and do the cosine for every single Riemann step that we do. And in principle, if we're taking an actual integral, it will be an infinite number of infinitely narrow steps. So we can expand this out a little bit. It is, in fact, the integral of f times the cosine of the angle between f and the direction we're going, integrated over x. So that's the way we're going to do the integral of f dot dx, where this is a differential distance. So what we can do now is we can take some complicated path and we can say at every instant there's a dx. That's the way that path is going. And if the force is some direction, like this direction or so, then every little bit of this, it's like a Riemann sum. We can be taking an integral. We can do distance vector, and that's our force vector. What are the requirements on this angle theta for work to be greater than 0? What do you think?
There has to be a...
How big can that angle get for work to be positive?
Up to 90 degrees?
Up to 90 degrees. So theta must be less than 90. So we're about to talk about work. And last year, we defined work to be F dot D, which in our case was F times D times the cosine, not of theta, but the cosine of the angle between F and D. So this year, though, we're going a step beyond, and we're going to say that work is, well, you've seen some calculus, right? Work is fine, work now. So this leaves us a couple possibilities. I mean, I guess it's 3 possibilities. The possibilities are this. We can have work greater than 0, we can have work equal to 0, and we can have work less than 0. Work is greater than 0 if the force, let's say it's this way, is... Ooh, how are we going to do this? How are we going to do this? If that's our